Hello everyone, I'm just recording my video for Homework 6 Problem 2 right now. This was definitely an interesting problem. At first I was struggling a bit with the material and just like all of the matrices, transposes, inverses, but then after this homework I started to feel a little better. So the problem setup, I mean these are kind of the same problem. We derived the 3-1-3 rotation matrix and then the B matrix. And then we're going to use that in problem 2 to solve for the dynamics of a spinning top that's asymmetric. So that does mean that in our inertia 1 and inertia 2 are going to be equal to one another. And then we just have that third inertia to account for. So first I started by getting my equations for all of our angular velocities, omega 1, 2, and 3, which I got from the inverse B matrix here from like this definition of the angular velocity vector. That gives me three equations, W3, W1, W2. Uh, then I go ahead and plug those into the kinetic energy equation, which is just going to be 1 half IT times W1 squared plus 1 half IT W2 squared plus 1 half IA W3, because three axes corresponding to three separate velocities. We go ahead and solve both of these equations out for their squares and then add them, which gives us this pretty simplified term, sine squared theta yaw dot squared plus theta dot squared. And then, so that ends up becoming our kinetic energy. We have this term with the IT and this term with the IA. Then we need the potential energy. We're told that our center of mass is a distance L away from P along the B3 axis. So we can just take that as our mass, gravity times L projected onto that B3 axis. So we just have the vertical component. Then we go ahead and subtract them to get the Lagrangian. That just gives us this term. I don't think you can simplify this much further, maybe with the square, but so this is our Lagrangian. Then we go ahead and do the typical Euler-Lagrange stuff, and we immediately find that dl d phi and dl d psi are actually zero. You know, the Lagrangian has no psi and it has no phi in it, so that means they're zero, which in turn is going to mean that our dl d phi dot and dl d psi dot are both constant values. And what that tells us is that these coordinates are ignorable and we'll be able to solve for them and plug them back in using the Routhian procedure. But first, we also find that d theta does show up, so this is not constant. We solve for dl d theta dot and then take the d dt of that, which is just going to give us it times theta double dot. Then we take the dl d theta of this whole thing, which was a little more annoying. You have that sine squared term, that cosine theta, and that's to the yaw dot to like account for, and then the MGL. But ultimately, this is what we did as our really our like only true equation of motion. Like we have these, but they don't describe this. They tell us the system's not accelerating. So then for part B, you know, because we found that DLD psi and DLD phi were zero, we know both of those are ignorable. The Lagrangian doesn't depend on them. Then when we actually go to do our Routhian reduction, first of all, we start by taking this DLD psi dot and DLD phi dot and just kind of putting all of that into a symbol. So this whole equation is equal to B psi and B phi. These whole equations. Then we're to define some constant a, which is just this equation divided by it. So that's where this like sine squared theta psi dot term comes from. And then we have this plus b cosine theta. And this b comes from our second definition, where b is just defined as b phi over it, this equation, which is the same as it over IA over IT omega 3, which as you can see is the term we have here. So then this all ends up becoming this equation for A. Then we go ahead and write this equation out in terms of psi dot, because we're going to eventually go and plug that back in into our real equation of motion. So we solve it for psi dot. We repeat the same process, but for phi dot, because we have the equation for omega 3. So we essentially want to eliminate that from our phi dot definition when we solve this equation out. Set them equal to each other, and we get an equation for phi dot. Then we just go ahead and, you know, plug that back in. We plug in that psi dot squared, which gives us this term. We plug in that psi dot normal here, and then that gives us our equation of motion for the system, depending only on the non-ignorable coordinates, so the coordinates that were actually there. So that was my video. I went maybe a little fast, but overall not too bad. Just a lot of like keeping track of different things and some algebra, but not too bad. Please let me know if you noticed any mistakes or anything that I made.